Yeah, our next speaker is Gary Seider. Gary is the engineering manager at Hubbell Power Systems. He's a registered professional engineer, has a BS in mechanical engineering from the University of Missouri-Rolla. He is a member of the American Society of Civil Engineers, Deep Foundation Institute, and is a past chairman of the Helical Piles and Tiebacks Committee. Thanks, Gary.
Thanks, Aaron. Yeah, BSME, some years ago, I've been, more working within the helical piles and geotechnical group for quite some time now. So appreciate the opportunity to come here and give this presentation. I call it kind of a work in progress or an interim report on some research we've been doing. And this is, as Aaron just kind of summarized there, a collaboration type effort between, again, private industry and academics, and also with government entities, DOTs, et cetera. We always like to extend that same type of collaboration, working together and partnerships. And so that's something that my company is very interested in. A little bit about us, Hubbell Incorporated, may or may not heard of Hubbell Incorporated. It's a multi-billion-dollar corporation. It's based out of Shelton, Connecticut. However, we have many different locations, mostly in North America, multiple states. I'm from Missouri or Missouri, depending on what part of the state of Missouri or Missouri you're from. So we have manufacturing facilities there. They're also in the Carolinas. There's facilities in New York, Canada, Tennessee, Ohio, Alabama, several different places throughout North America. We also have facilities in Juarez, Mexico, and also in Canada, St. Jerome, Canada. We basically break down Hubbell Incorporated into two different types of product groups. There's electrical and electronic components. I would be mostly associated with the second group, which we call our power utility products. So in this case, we're going to be talking about steel foundation products that are used in the power utility industry, but also in the civil construction industry as well. So you may have heard of some of our brands. There's Hubbell Power Systems, Chance, and so you may hear us say the word Chance anchors or Chance helical piles. That's the brand name for it. Chance comes from previous company. Albert Bishop Chance was the namesake of the company that I currently work for. Aclara, you may have heard of Aclara or Killark. Progress Lighting, so in some cases we do a residential type work. Quasite, so those are just some of the brands of Hubbell. And again, it's a very large corporation. Before I continue, I'd like to recognize a couple of individuals. One of them is Peter Morrison. He's online with us, I believe, at least I hope so, listening virtual. And he's one of the individuals, again, from a private contractor basis that kind of connected us together, as I'll mention here as we go forward. Also want to mention Juan Sebastian right here. Juan Sebastian is a graduate student. He's works currently for Dr. Gallant here at UMaine. He is a graduate student here at UMaine. He is currently back home in central Missouri, sweating his tail off, working probably as we speak. He's probably sitting under a canopy with his computer up, and he's running probably either a torsion test or a lateral load test, as I'll show you. It has actually gotten a little cooler back home, so I'm enjoying the weather now, but it's been a little bit better back home. So anyway, I will continue. So when we look at this type of ideas and we come together, from a corporate standpoint, so I'm a little bit different perspective than some of the presentations that you've seen here and over the past day and a half. I'm going to look at this more from a value prop, is what we refer to it as with respect to a manufacturer of products, particularly in this case, steel foundation products. So this has really been a collaboration, again, between Hubbell Power Systems, TIDC, and then contractors at this point. And it was originally based upon some work that was done by Dr. Gallant with respect to laterally loading various types of anchorages, particularly for moorings. And so Peter Morrison, he's with this company called Helix Mooring, which is located in Maine. I forget exactly, he's going to get mad at me, but it's near Portland. He he was aware of it. I think you attended a conference perhaps that Aaron, you were at. And so we all kind of got together back in the spring of 2020. Everybody remember what happened in the spring of 2020? So this was all kind of interesting how we came together virtually for a long time. And but we put together eventually got to a proposal. So the need here is, and we're going to talk about helical piles. So if you're not familiar with that, you're going to see a few examples of them in this presentation. They're a steel foundation product that is screwed into the ground. It's very effective at transferring axial loads, so tension and compression type loading. Depending upon the geometry, it's not as effective resisting lateral forces because it's a generally slender foundation element. So what we're needing often is an augmentation type of situation where we're trying to increase the lateral and torsional resistance of a helical pile for different applications, signage, roadway lighting, different types of, roadway signs and lights, things of that nature. So area lighting, but also for moorings. And this could be aquaculture. So offshore moorings, boat moorings, various mooring fields, anchorages of virtually any application as you can imagine. And then lighting foundations, et cetera. So it's an application that's very extendable to different products. So with the help of Dr. Glant and also with Dr. Bradshaw, we put together a research proposal through TIDC. Got it approved and funded, and we're well on our way. We're now into basically our second year of this work. And what we're working on, as I'll show you, as this add-on modular component of a collar vane that is added to a helical pile. So this, again, is what we're currently working on, based upon that work. So phase one, which I kind of say is complete, it was mainly done last year. This was done back, again, where I'm from in mid-Missouri. And we put together different types of concepts for this collar vane. And we tested it in the soil conditions that we have in our part of the world, which is basically a medium to medium stiff clay. And just to give you a sense of the efforts involved so far, we've calculated we put in over 1,200 man hours to date on this project. So a lot of work by a lot of my engineers and co-op students and Juan Sebastian to do the installations, testing, et cetera. And last I calculated about a month ago, our total in-kind contributions in dollars is about 160K. So this is not an insignificant amount of money and efforts that are going into this type of work. And we are so far getting pretty positive results with this. It's led us to some changes, as I'll mention later on within the designs. So we're currently into phase two right now. As I mentioned, Juan Sebastian is currently in Centralia right now doing the work. And he is starting to do more testing on what we call a redesigned collar vane, which has led from the work that was done last summer. So it's more of a one-piece modular type of application. So again, part of the value prop here has to do with comparing conventional methods of what I would call a steel or a drilled shaft, concrete foundation, which is very common in the industry. And so I'm going to jump through some of these steps. But here's a simple example of a lighting foundation. But again, it can be in multiple types of products, signage, or even buildings, where in order to build the foundation for this element, you need to drill a hole. You need to put in a cage, concrete. This is basically a form for your anchor bolts. So you have to set that form and then time, of course, in terms of then having a foundation that is now ready to bear load. With a helical pile, which is what you're seeing here, which is typically an extendable element that has these plate elements that act as the means of installation. They're a screw, and then you can add sections to it then to extend it to whatever depths you need. And in those situations, installation's a little more straightforward. You have this kind of a rig here, if you can see it, again, variety, but this is what we call a digger derrick truck. Literally screws the foundation into the ground. Once it's in place, it's ready to bear load. So again, much faster. Some of the sense here on this slide of how, the types of production rates that are capable of this. if some of you in the DOTs may be aware of steel foundations because they are used quite often in that space. So advantages are there. So what we're talking about is at this portion of the helical pile is adding that collar vane, which you'll see here. So our original concept or phase was this modular, we called it the two-piece collar vane. Now, collar or shear vanes is another term for this. They're not new. The idea of a shear vane has been around for years as a means of bearing lateral forces in soils. What's unique or a little bit different about this concept is how we're connecting it or interacting with the helical pile itself. So, and this is our original concept. You can see how we had this kind of broken up into two pieces with these four, the assembly making up the four vanes. And so this is a sequence of installation. This is the helical pile progressively being installed, again, screwed into the ground. And then the vane is added to the shaft element, bolted together and installed into the ground so that the pile is rotating, but the vane is not, it's static. It's just basically being pulled into the ground. I'm going to show you a quick example of that here in a minute. So that your final element is in the ground. And then the part that's somewhat different about this approach, as in the past, is now we're connecting the vane. We're structurally connecting the vane to the shaft at this point here where there's a bearing plate. So it's kind of hard to tell, but over here on the side of this slide, that is a 2-scale type representation of a helical pile on a collar vane. So if you can imagine, this is about 20 feet overall length. So your collar vanes in this case is representing somewhere around 3 feet of overall length here, up down to this, to the prismatic portion or the tapered portion of it. So, and you can see some of the photographs of some of the guys as they're doing their work here. And this is, hopefully, I'm not sure how to make this video work, but can you do it? Okay. So we're going to show you how this video of this installation goes. Not the second one. There's an embedded video into this one, Aaron. Sorry. Sorry for tripping you up there. Just go back. There you go. So it's embedded in that slide. There it goes. So that's the pile being turned, and then now it's making contact with the top of the vane. Now this guy in the back here with that crescent wrench, he is just basically making sure the vane gets seated, because before it gets seated into the ground, it would have a tendency to rotate with the pile. So he's just making sure that he's keeping it steady. He'll eventually take that off. But that gives you an idea of the rate of penetration. And so you can kind of see how it's being pulled in. So the plate elements themselves on the helical pile are doing the work. They're pulling this vane into the ground. Eventually he'll take that thing off. But parts of what we monitor when we install piles is rate of penetration. And also this device here is a torque indicator. It's actually measuring that effort of resistance that it takes to put the pile in. And that's also very useful. Another reason why we are being so careful with controlling the vane is because Juan Sebastian has to have everything specifically lined up with his strain gauges and his strain pots to make sure that we're measuring the various stresses and displacements correctly. So you can see how it continues to go into the soil. Gives you an idea, again, of the rotational speed as well. It can be a little faster than that at times, but that was basically a good sense of. Now that vane, I can't remember if that was a 2 foot or is that that's a 2 foot diameter vane, but I think it's 3 foot. It was one of the 3 foot elements. So it gives you a sense of what we're talking about. All right, thank you. So is that the next slide? Okay. So get into a little bit of the setup and what we're doing. So this is a little bit of nuts and bolts, a little bit different than perhaps some of the presentations you've been seeing so far. But this is the lateral load test. This is the setup. So here again is your helical pile with the collar vane in place. And the assemblage that has a sets of load cells, actual load cylinders, and then a string pot in order to measure displacement over here, connected to a reaction anchorage. Again, this is a helical anchorage. And this is, set back at a distance so that we can resist the forces. So here's your plan view and then a top view. And so it's a pretty good picture. You see the two load cylinders applying the lateral load. The helical pile with the vane is back here, load cell here. And then, so we measure that, the pressure to establish load. And then also, of course, the cell is measuring load. And then the string pot is back on this back side. And that's how we're measuring the displacement, the lateral displacement of the pile. So here's some of the, some of the data that we've been developing over the course of the studies. And what you'll see here is that the vanes, the diameter of the vanes is between 1, 2, and 3 foot. Essentially was our diameter of our vanes that we checked. And then the lengths was either 1 or 2 or 3 foot lengths. And so basically what this slide is attempting to show you is that if you go with a situation where there is no collar vane, the shaft itself, which is relatively slender, it's only 3.5 inches in diameter in this situation, its lateral load resistance, this is a function of deflection, and the load in kilonewtons is relatively low. And it's not generating a whole lot of lateral resistance, which is expected. That's part of the issue, is we were trying to add a modular means of adding lateral resistance. So the red ones here are basically the 1 foot, and then you get into the 2 foot diameter, and then and then you get into the 3 foot diameter vanes, and then their various lengths. As they get longer, of course, you're resisting increasingly greater lateral load. So you get into the 40 to 50 kilonewton lateral load resistance, which in the applications we're looking at is pretty good. This slide demonstrates that for 1, 2, and 3 foot diameter vanes, this normalized force lateral resistance. So 10 times, 20 times as much lateral resistance as without the collar vanes. You can see how just even something 2 or 3 foot long vane can make a tremendous difference in terms of lateral resistance, which is again what we're shooting for. This slide is demonstrating one really great aspect of this, which is what excites us with respect to them as a manufactured product, that we can create a modular collar vane that can be adapted pretty quickly and easily, cost effectively for our contractors. So what we're demonstrating here is for these, if you look at these 3 slides, these are representing actual moments or bending moments within the shaft of the helical pile. We instrumented these shafts with the great help of Keith back here. Keith Berube helped us instrument these and run these tests. So you're seeing different amounts of bending moment within the shafts. And what's important about this is the amount of resistance, or how much actual stress or moment is in the shafts compared to what it would be if the collar vane was not resisting those lateral forces. So it's hard to tell, but these little dots here at the top are representing what the moment in the shaft would be at that particular point, which is pretty close to the load application point, if the collar vane was not there. And basically, it's not plotted here, but if we did plot it, the moment in the shafts, if the collar vane wasn't there, the moment, it would greatly extend out beyond that, the current scale here, to the point where it would greatly exceed the allowable bending moments of the shaft. So the point being here is a couple of things. This is the 1 foot, the 2 foot, and the 3 foot vane. It's transferring the loads, further. It takes, it's the amount of mobilization of that load it's extending deeper into the ground based on the collar vane length, but also the magnitude of the moments is way below the allowable moment of the shaft, which is great. That's what we want to do, because there are benefits to having slender elements, particularly when it comes to axial load. So this is something that will make it very modular for us as a manufacturer, and gives us the ability to add this to projects as needed. So that's the nice thing about this for us. And it really comes down to that connection, that connecting the collar vane to the shaft, that structural connection. Another kind of way to look at it or consider it is the vane resistance versus the shaft resistance. And if you look at this, basically CV3-3 is basically representing the vane. It's 36 inches or 3 foot diameter times 3 foot long. It's carrying 85% of the load, that lateral load, at about, in the case, it's 15 inches, or I'm sorry, 15 millimeters of displacement. So that's very impressive. that collar vane, relatively small in terms, you can say relatively short lengths, taking a lot of load. So we also did some torsion tests. Dr. Gallant said, hey, let's do some torque tests on these things as well, because the vanes would contribute greatly, and there are applications where this is important. And so plan view of our torsion tests, where we just basically created this nice long moment arm, relatively rigid, and connected it on each end with a separate load cell hydraulic cylinder, so that we could then apply a moment to the shaft of the pile right here. And so you can kind of see that here, the load cylinders here, and the load cells back here applying that load. So, and again, these are connected out on the ends with the helical anchorages, much like what you saw before. So directly applying that torque right here. And then we had a series of string pots measuring deflections on the ends of the arm and also directly on the vanes, because we found differences in performance and stiffness relative to where we were doing that. Where we were measuring that load. And so this is kind of a brief summary, if you will, of some of the load test results. Again, the 1, 2, 3 meter or 1, 2, 3 feet diameter vanes, and then the 1, 2, and 3 feet of length. And as you'd expect, the greater torsional or moment or torque resistance is with the vanes that are the longest and the largest diameters. So that's, and one of the things that we found out with the previous design, that modular design where we bolted them together, is that there was some differences in how the vane responded to load based upon the connections, the structural connections. It wasn't as stiff as we thought it might be. And so that's one of the reasons why we changed the vane to more what we call a one-piece vane, which is what we're doing today. And so that's, kind of where we are currently. And Aaron, if you could cue up that video, I want to show you one more thing. And the reason I want to, well, a couple of things. First of all, a lot of discussions today about composite materials, recyclable materials, FRPs, and that's great. I just want to, steel still has a place in our infrastructure. Steel is the most recycled material in the world by far, hands down. A lot of these products you see here, these steel foundation products from Hubbell Power Systems, they are in some cases almost 100% manufactured from recycled materials. And in some situations, particularly with DOTs, it's vitally important that materials be sourced domestically. So melted and manufactured in the USA is a big deal. And that is certainly the case with these helical pile products. So just want to make sure everybody recognizes that there is obviously a place for it. And so that's one of the spiels or pitches, if you want to put it. So last thing I want to do is that in my entire working career at Hubbell Power Systems, this has never happened ever that I can ever remember. You talk to Dr. Bradshaw and Dr. Gallant, they'll tell you that, over the course of the last couple of years, we've been discussing where and how to do these tests. So we certainly had a perfect site for doing these in clays, because back where I'm from, we have a very uniform, consistent clay. It's a medium to stiff clay. And the question always was, we got to do this whole set of tests again in a different soil type. And so we'd say, what's the natural different? We got to go to some kind of a non-cohesive, sand or granular materials. And so initially our plans were, we're going to go to Rhode Island, or we were going to go different places like that to do the tests. Now, if you're familiar with doing testing with this equipment, mobilizing all that equipment and mobilizing staff, when you're doing tests over the course of about 6 to 8 weeks, which is what this is taking typically, the length of all these different tests, that's a lot of money and just a lot of cost. So we were saying, what other options do we have? And so we said, well, can we just build our own sand site in Centralia? Because all the equipment, my staff, all this instrumentation, bring Juan Sebastian back to Centralia, and can we just do it that way? Just make our own, literally make our own sand pit. And so we got bids. Shocked us how much it was going to cost. I pitched it up the chain. They said, yeah, build it, spend money. Never happened in my entire working career at Hubbell. But we're at a situation now where it's somewhat unprecedented. They said, go ahead and spend the money. We had to obviously justify it. Everything's on ROI, as we know in our lives. And we're able to do that. And so what I want to show you here, it's about 1.5 minutes, is a time-lapse video of building the sand pit, which we are currently using as we speak. So Aaron, go ahead. So it's very quick, but it's a time lapse. This was shot with a GoPro camera. So this is back, that's the sand, the clay soils that we have in our part of the world. So minimum excavation depths was about 8 feet, was as deep as, some areas are a little bit deeper. And so here they're going through the compaction efforts of the sand itself. We added a drain so that we can control the groundwater levels over time within this site. We're going to use it for more than just color vein tests. You can see the guy back there in the corner. He's building the drain over there. Very quick, as you can imagine, but they're doing all their vibratory compaction. Always fun to watch people go fast, right? But GoPro cameras are great. I mean, you can just set it up in the same spot and come back and piece it together later on. And they built the access roads for us as we asked them to, with gravel. Had it set, and that's finished product. So that was conceived of probably in June or so, and the lion's share of that sand pit was built in July. It was actually, they put out the seed and the straw for the just the landscaping area, I think on Monday or Tuesday of this week. So it's brand new, and again, we're testing on it now. So anyway, thank you very much.